course. Well, welcome to the biweekly SPCL BCAS seminar. I'm very, very glad that we could convince Aparna to tell us about the latest developments in deep learning, especially for solving PDEs, which is one of the newer things that she has also written a Science News article about, and many interesting things. Let me just give to Nikolai to introduce Aparna.
Okay, thank you, Torsten. And again, thank you, Aparna, for agreeing to give a talk. Aparna is an associate professor at the University of California, Irvine, where she leads the HPC Forge lab that focuses on high-performance computing, computational science, and AI. And by the way, that's a really neat lab name. She received her PhD in computational science and engineering from Georgia Tech, and subsequently worked at the MIT Computer Science and Artificial Intelligence Lab on exascale software. She has published numerous papers on high-performance computing, deep learning, and computational science. And without further ado, Aparna, please take it away. Thank you.
Thank you, Nikolai and Torsten, for the good introduction and also the warm welcome. And thank you for having me on this online seminar. It's really nice during this pandemic, since you can't travel, you can do these online seminars. So it's very exciting. And thank you for organizing that. So yeah, today I'm going to talk about some of the recent work that we've been doing in my lab for the last about 3 years now in using deep learning for solving PDEs. And we know that PDEs are ubiquitous and used for analysis, modeling, and optimization for complex systems. And today, if you want to solve PDEs, the most common and traditional way is to use numerical methods, such as finite difference, finite volume, and finite element, and so on. And the HPC community specifically has spent the last several decades trying to improve the performance and scalability of these numerical solvers on large-scale systems for large problems. But they still remain today computationally expensive. So I won't give you too many examples. I'll give you one example. So here is a study from NASA, it's the CFD Vision 2030 study. So they came up with this few years ago. And what they essentially did was identify 4 grand challenge problems we want to solve by 2030. And they also kind of summarize 7 findings. So here I'm highlighting 2 out of those 7 findings. So one is that HPC hardware is progressing rapidly, and the technologies that will prevail are difficult to predict. And what we are seeing is that the HPC hardware is getting more and more specialized. And these traditional numerical solvers, they have been ported onto, let's say, GPUs and so on, but there's still a lot of work to remain, and they're nowhere as close in performance and scalability as they are on CPUs. And the second finding here is that revolutionary algorithm improvements are required to enable future advances. And we do need to figure out how to map or design new algorithms that can actually take advantage or exploit these emerging hardware capabilities. And although there's work being done here, we're still quite far away. And to give you one example, one of the grand challenge problems here, the first one is the, I don't know if you can see my pointer or my screen, is the large AD simulation of full flight envelope. And the study estimates that to achieve a 24-hour turnaround time on this wall model large AD simulation of the full wing at a high enough Reynolds number that's sensible requires almost 180 petaflops per second. And this is only achievable on the most powerful supercomputer today, which has several GPUs, and most of these simulations are not very good at taking advantage of that. And this is for one configuration. And this is assuming that this simulation is running at a high efficiency, which is not. So we still are a long way to go to enable these kinds of challenging problems. And moreover, this makes it very infeasible to do things like uncertainty quantification. Or if you want to do airfoil shape optimization, we want to do many different simulations. These become intractable today. So what else can we do? So on one end, we have the finite element, finite volume, finite difference methods. They have very high accuracies, require very few parameters and small amount of data, which is nice. It works well so far. On the other hand, we have the deep neural nets. And these are typically over-parameterized, require a large amount of data to train reasonably accurate models, and typically don't have, at the extreme end, don't have any physics baked into them, right? And unlike computer vision or natural language processing, scientific machine learning has its own unique set of challenges. So one is, in many of these simulations or many of these problems, PDEs we want to solve, there's a huge cost to data collection, especially the amount of data that's available. High dimensional data that is available is rather limited. And if you want to collect this data, it becomes quite infeasible to do that. And the other is we want these models to be physically accurate. That is, we want them to conserve physical quantities or somehow encode the underlying physics or constraint to be meaningful. So the question is, between these two extremes, there are many designs in the middle that are possible for these deep learning algorithms and models. And I'll point out a few of them. So on the left hand, closer to, this is still a deep learning model, but closer to the amount of physics that it embeds, is this work by Julia Ling. It's one of the first works of deep learning model that came out, where the idea here was the physics is baked into the neural net architecture, which has very strong inductive bias, right? And then, so these are fine, but they're very restricted to the kinds of problems they can solve. And then in 2019, there was this other model that came out, which is the physics-informed neural nets. This is very, very popular today. There have been several papers written on top of pins. And here the idea is that the physics is imposed by constraining the output of the neural net to satisfy the PDE. So instead of baking the physics into the network itself, you constrain the loss function here. So you regularize the loss function and you penalize the model if the PDE is not being satisfied. So this has a weaker inductive bias. But if you look at the loss function here, you have to both fit the data and you also have to, in some sense, satisfy the PDE. So you have two components to the loss function. And here it's not shown, but in some cases, these two loss functions can be in completely different, have different contributions to the total loss. So you have to kind of have some hyperparameter to tune the contribution of each loss. So because of these multiple loss terms, these networks are in some sense slightly harder to train, and they're also more expensive to train because the physics regularization loss usually requires computing derivatives. So you have to do automatic differentiation in your backward pass, and that can take a lot of time. So these networks are a little bit harder to train, but the nice thing is they are more generalizable than when the physics is baked into the network. And in the third case, the idea here is to build a model that is generalizable. So you don't have any physics baked into the model. Then you couple the neural net model with a physics solver. So it's not a pure surrogate, but it in turn acts more like an accelerator in solving these problems. Right? So there are different designs possible. And developing these kinds of solvers is still pretty much in its infancy, and there's still a lot of work to be done if they were to reach accuracies on the order of these traditional numerical methods that have been developed for over half a century. So what I want to do today is I'll first talk about our work in designing deep learning models that work more as an accelerator than as a pure surrogate. So they're coupled with a physics solver in accelerating PDEs. And then the second part of my talk, I'll talk about more of our ambitious goal of designing pure surrogates that can compete with, that can essentially replace the traditional solvers and not just augment them. So first I'll talk about a simpler version of the problem. And this is work done by my PhD student Octavi, joined with Abhinav and Nicholas from AMD Research. So when we started doing this, we first looked at, okay, so what is current state of the art in applying deep learning for these class of problems? So we looked at 10 different parameters. And one of the first things that we noticed is that many of these deep learning models, they predict the output variables mostly as a pure surrogate. So in this case, the challenge is that the output of the model may not respect the convergence constraint of the original physics solver. And that's what we see here. So in the last column, meets convergence constraint, half of them don't meet the convergence constraints of the original solver as a pure surrogate. And the other issue that we saw, the other factor is that in many of these cases, the test geometry was a subset of the training geometry. So they're not being tested or limited to geometries that have been seen in training. So one of the things we wanted to do is create a model that was generalizable to a much larger class of problems, and not just to the geometries that were used in training. And the third challenge here is that when we're especially dealing with more challenging flows, such as turbulent flows, you have, in addition to velocity pressure, you're also trying to predict some turbulent fluid quantities, such as viscosity and so on. So in this case, some of these quantities can have very vast different range of values. So most of these approaches tend to predict one or a subset of the variables that are in the same range of values. So when we have to predict flow variables that are vastly different range, and require some special treatment. So how do we actually do that? Predict multiple variables, but using the same network. So what we came up with is what's called CFDNet. So the idea is we wanted to, most of these prior work, they satisfy 7 of the 10 parameters that we looked at. And we wanted to be able to satisfy, both be able to predict on unseen geometries, predict multiple flow variables, irrespective of the range of values they have, and at the same time meet the constraints of the physics solver, so it can actually be used in solving PDEs today, right? So it's CFDNet can be used as a surrogate, but it works, as I show you, better as an accelerator than as a surrogate. So here the idea or objective is to learn a function G. So G is essentially a map from, so here G is a map from any intermediate flow field to the final steady state solution that we want to predict. So essentially the goal is if G can somehow short circuit the iterative process and act as an accelerator. And here xn, xi, these are tensors of Z flow variables, is the variables that we want to predict on an m by n grid. So this is a 2D domain. And we choose for this work a convolutional neural network as a candidate for G. And we expect that the CNN in this case would be able to capture the nonlinear, the multidimensional relation present in PDEs such as Navier-Stokes, like nonlinear equations through the nonlinear activations. So that's the high-level problem formulation. So what is our input? So since we're using the intermediate flow fields, we can somehow harness the image nature of our grid. So there's a one-to-one mapping between the grid dimensions, each cell in our grid to a pixel in our input image. So you have an m by n image. So this is for velocity component. And then we augment this grid with the values of the boundary. So given the values of the boundary, you have a unique solution for if your problem is closed. And then depending on the number of variables you want to predict, in this case, we want to predict the velocity in the y direction, pressure, turbulent viscosity. We can stack up all these different images, and that creates a tensor of size m plus 2 by n by z. So that is the input. And I mentioned before that some of these variables can have vastly different range of values. So here, to give you an example, the velocity can go from 0 to 1, whereas the turbulent viscosity can be completely orders of magnitude different from the range of the velocity values. So what happens in this case is that when you train a network without any special treatment to the input flow variables, then we can have some of these flow parameters, since they're significantly smaller than others, they become negligible in some regions of the flow and just disappear. So what we do is we non-dimensionalize the flow variables to actually improve the learning task and have a single network be able to predict all the different variables. So our network design, our input and output, in this case, are the tensor that I showed in the previous slide. And they're the same dimensions, except that the input is the flow at some intermediate iteration, and the output is the value at the steady state. So the network here is a 6-layer deconvolution network. So first 3 layers are convolution networks. They essentially reduce the dimensionality of our input to create this abstract representation, and from which we recover an output which is the same size as the input. So the first and the last layers here are parametric ReLU, because we have to capture negative values in our input and also to predict the real valued output. So pretty straightforward network, nothing too fancy there. The key idea here is the framework. So the CFDNet framework is not a pure surrogate, but the goal is to build an accelerator, so to have the same solution as a numerical solver. So we don't want to replace a solver, but essentially augment the solver. So here the idea is to have a physics solver, CNN physics solver coupled framework instead of a pure surrogate. So since the CNN model itself as an input does not take into account any boundary condition value or any domain information, to be able to predict for different flow problems, we need to somehow embed the domain information into our intermediate field. So what we do here is we take the initial field given by the user, and this initial field has, this is domain agnostic, it has no domain specific information. So what we do is we do a warm-up. So essentially run the physics solver for a couple of iterations, and I'll show that this warm-up essentially only takes about 1 to 2% of the total number of iterations of the solver. So it's very, very fast, right? And so, but what this warm-up does, it's very critical. So what it does is it essentially allows the fluid parameters, the boundary conditions, to interact with the geometry. So the intermediate solution, the intermediate flow field to the CNN model actually captures the domain information. So without doing the warm-up, then our CNN model will be predicting from a completely random initial guess, and the model will be not very good. And I'll show you that. So this warm-up, even though it's very cheap, it's very critical. And then we take this initial, after doing the warm-up, we take the output of the warm-up and then feed that to the CNN model. Then you do the inference. And the hope is that this inference produces a steady state output. But since the CNN model does not constrain the physics, it does not either bake the physics or constrain the loss function, it's possible that the output does not satisfy the conservation loss. So to make sure that we actually have a physically meaningful solution, we then do some refinement. So run some M iterations of refinement until the convergence constraints are reached. So we have the same solution as the physics solver. And the hypothesis here is that if the CNN model was successful in short-circuiting the simulation, then the sum of the warm-up and the refinement iteration should be significantly smaller than if you had to use just the physics solver. So it acts like an accelerator. All right, so how do we actually evaluate this CFDNet? So we looked again at the related work, and one of the things we noticed is that it's very hard to compare against related work because everyone uses a completely different loss function or error metric for evaluating their model, and also different data sets. So unlike in computer vision or natural language processing in these domains, we don't really have a standardized data set for comparing these different models in scientific machine learning. So that is one of the challenges here. So what we essentially ended up doing is to have a dual convergence criteria. So we use a combination of residual convergence plus satisfying the conservation properties to ensure that our solution has essentially the same result as the traditional numerical solver. So we evaluate this CFDNet on 2 case studies. The first is a wall-bounded flow. So essentially this is turbulent flow in a 2D channel. And this is useful for pipe designs and so on. And the second is external aerodynamics. So this is a little bit more challenging. So in this case, we want to predict turbulent flow around solid objects, such as like an airfoil or a cylinder. And in the second case, we want to be able to predict flow. We train on essentially ellipses. So it's just very simple geometry. It's very easy to create glyphs for ellipses. But what we want to predict is on geometries that we haven't seen during training. So in this case, we want to predict on an airfoil, which has a very sharp edge in the tail, which the model has not seen. So the ellipses don't have any sharp edges. And we also want to predict on things such as a cylinder. So even though cylinder looks like a special case of an ellipse, the flow in the wake, the rear of the cylinder, you have a large recirculation bubble, which does not show up in any of the ellipses. So there's physics in these training geometries that don't show up, in these test geometries that don't show up in our training geometries. So in the case of the channel flow, what we're trying to essentially see is keep the geometry the same, but we're changing the boundary condition and the flow conditions to see how well we can extrapolate. In the case of the external aerodynamics, we keep the flow conditions the same, we're changing the geometry to see how well we can generalize to different geometries. And in all these cases, the Reynolds number are kept high enough so the flow is turbulent. So what the equations we're trying to solve for testing CFDNet here is the Reynolds average Navier-Stokes equation with a one equation turbulence model. We use the OpenFOAM solver for creating the training data set. And we train on a GPU. It's pretty standard. The one thing here I want to mention is that since the goal is to use CFDNet as an accelerator, when we run the OpenFOAM, we turn on all the other acceleration techniques that are pretty standard when running numerical solutions. So we run with the GAMG, the multigrid solver. We also use the Gauss-Seidel smoother as from the OpenFOAM. So all the other acceleration techniques that are typically used are turned on as well. So we're trying to see how well CFDNet can do on top of the existing current numerical acceleration techniques. So here are the results for the channel flow. So we can see here it's qualitative results that CFDNet does quite well as the OpenFOAM solution. We're able to capture the non-slip boundary condition. And in this case, we see that it actually performs quite well as just a pure surrogate when the geometry is kept the same and we just change the boundary condition of the Reynolds numbers. But in the case of the external aerodynamics, so on the left, we see the results for the airfoil, on the right for the cylinder. When we just do warm up and inference without doing any refinement, the solution is not yet converged to the final, the physics solution. So we have to do a warm up to get the same solution as the physics solver. So it's pretty good, but it's not good enough. So especially in the case of the cylinder, we see that in the wake, there's still a lot of error that needs to be resolved. So the physics is not fully resolved. So we see that it performs better as an accelerator than as a pure surrogate. And these are some of the performance numbers. So the first bar here shows the CFDNet with warm-up inference refinement. The second bar here is if we don't do warm-up, if we directly take the initial user-given input and then pass it to the network and then do refinement, that's the second bar. And the third is the traditional OpenFOAM physics solver. And across the board, we see very good speedups as an accelerator. And this is accelerating on top of already all the numerical acceleration techniques. And the solution is good. The one question here is that why is the performance for, if you look at the airfoils here, we see that the speedups for the airfoil are much better than for the cylinder. So one thing to wonder is, okay, cylinder seems like a simpler geometry than an airfoil to predict given the ellipsis. But as I mentioned earlier, there's a large recirculation bubble in the wake of the cylinder, where the physics is much harder to resolve. So it takes a lot larger number of refinement iterations than in the case of an airfoil, which was also quite surprising for us. The second point that I want to mention is if we don't do a warm-up, so in the second bar, the middle bar here is if there is no warm-up done, so where we don't let the boundary conditions and the geometry interact with the physics solver. So if we don't do the warm-up and we pass in the initial flow field to the network, in some cases from the cylinder, we actually see a slowdown. And this is because the input has no domain knowledge whatsoever. And until the numerical scheme interacts with the boundary condition, we don't really embed the domain knowledge into our intermediate flow input. So warm-up is actually very important. So in these charts, the number in the brackets, that is the number of warm-up iterations we do. So warm-up iterations we do is very small. It's only a handful. It's like 1 to 2% of the total number of iterations of the physics solver, but it significantly improves the speed up anywhere from 2 to 5x because since our network input does not embed the boundary condition or the coordinates of the geometry, the warm-up is the way we actually implicitly input the new problem information into the input. Okay, so the other way would be to change the actual model input to actually take in the boundary condition and the coordinates as an input, but that would entirely change and it would make our model more domain specific. All right, so that's kind of my first set of spiel of CFDNet. And so far what I showed was the results on a 64 by 256 grid. So this is a pretty coarse grid. And in many cases, we want to resolve fine scale physics, which to have high accurate solutions. And in this case, we want to resolve fine scale physics. In many cases, we want to increase the resolution of the system. And when we increase the resolution, so here, this is time to convergence or flow around an airfoil. So as we increase the resolution, you can see that the time to convergence goes from anywhere from 10 seconds to almost 100 minutes. So this is a significant increase in the convergence time as we increase the resolution. And this is for just one airfoil case. And when we want to do airfoils, as say shape optimization, we have many different shapes and we have different configurations of the same airfoil. So we want to change the angle of attack, which is the angle between the chord and the incoming wind direction, or we want to sometimes change the pitch angle, which is the angle between where the airplane is pointed and the horizon. And in many cases, for example, the angle of attack controls the lift, airspeed, drag. It also changes the distribution of pressure above and below the airplane. So it changes the physics completely, and we might need higher resolution to actually resolve some of these configurations. So the question is, okay, we have a model that is trained on 64 by 256. How well does this model do when we change the grid dimensions? So this task is actually has a special name. It's called super resolution, where we want to reconstruct the fine scale flow physics from coarse grid solutions. So the question is, how well does this model do on the super resolution task? So we did this experiment. So we took the 64 by 256 model that we trained, and then we tried to apply this to different resolutions from 256 to 256 all the way to 2K by 2K. So up to resolutions 256 times larger than what we use to train the base coarse model. And what we see is this: the validation loss drops significantly, almost increases by almost an order of magnitude. So the coarse model that is trained does not do very well for this task of super resolution, and that's quite restrictive. So then we go back again, and since we did our CFDNet work, this field is very fast growing. So you can see that the new related work we did, there's a significant number of papers in 2020. So a lot of people are working on this problem. We're like, okay, what are people doing? So maybe someone has already figured out, solved this problem of super resolution. So we don't have to do this. So we looked at this, and what we noticed is that many of the CNN-based approaches, they're finite dimensional maps. So they map from one finite dimensional space to another, and they mostly lack resolution invariance. So unless they're trained with input resolutions of different inputs with different resolutions, they are not able to be applied to this task of super resolution. The alternate here is to use mesh-free resolution invariant DL methods, and there are a bunch of these that are using convolutional networks and using operator networks, which I'll talk about a little bit later in my second half of the talk. And these are one alternative because they don't use a mesh. They're mesh-free, so you can sample points from your input. But the issue we saw with most of these is that the training data, the way the training data is collected is by running a high resolution simulation and then downsampling that to a low resolution, and then that's fed into the network to train the model. So the problem is that it suffers from the same limitation as the classical CNN approaches, where you require a lot of computationally expensive simulation to collect your training data at high resolution. I mean, that is not really feasible for many of these problems, and makes your training extremely expensive. So we like CFD. So we saw that, okay, CFDNet is not so bad. The main issue is that it still can extrapolate on scene geometries. It meets convergence constraints, but the issue is that it's not resolution invariant. So how can we actually fix this problem? So we kind of extended CFDNet into what we call SURFNet. And the idea here is to eliminate the need for extensive data collection at high resolution, at the same time be resolution invariant and accelerate high resolution simulations on unseen geometries while meeting the convergence constraint. So here we primarily train the model on coarse grid data. So we still train the model on 64 by 256 data as before, but the idea is to transfer that model to a higher resolution. And I'll talk about how we actually do that. So the goal here is to eliminate large training data and at the same time achieve resolution invariance. So what we ended up doing is to use transfer learning, essentially to leverage the correlations that are inherent between the low and high resolution inputs in many of these turbulent flows. So what we see is that low resolution solution, they contain critical information. For example, the coarse grids, they're pretty good at capturing and resolving simple flow regions, such as flow in the free stream where you have small gradients. But what they're not very good at is capturing high gradients. For example, the wake behind solid bodies, or if you have a flow separation, they're not very good at capturing this. So the question is, how can we actually train the model using low resolution input to capture most of these simple physics, and then just refine the physics at regions where the coarse grid model is not able to do so well. So the idea here is, first we train using a large amount of low resolution inputs. We train a coarse model. So we pre-train a CNN model at a low resolution. And then what we do is we transfer that trained model to the target fine resolution. And when we transfer, we essentially take the weights of the coarse model, reinitialize the network, and then we do fine tuning at the higher resolution. And this fine tuning is done at a low learning rate because we want to make only small updates to the weights. And also it's done for very few epochs. So just a couple of epochs, 1 or 2 epochs, and on a very small high resolution data set. So I'll show that just using one geometry and the same geometry at all high resolutions, we can actually recover the fine scale physics. And we propose two flavors of transfer learning. One is one-shot transfer learning, so where you go from the coarse resolution, 64 by 256, to your target resolution, whatever it might be. If it's 2K by 2K, so you go from 64 by 256 to 2K by 2K in a single shot. And this works, but it does not work as well. And I'll talk about that in a second. So we also propose another variation of transfer learning, which is incremental transfer learning. So instead of going from your course's resolution to your target resolution, especially when they are so far apart, so 64 by 256 and 2K by 2K are like 256 times larger than the small. So the physics can be quite different when we go from such a low resolution to a high resolution in a single shot. So the incremental transfer learning essentially does learning step-by-step incrementally. So we can choose the step size depending on the problem, where essentially you go from, let's say, 64 by 256 to like 256 by 256, like 4 times larger resolution, and then another 4 times larger, 512 by 512, and so on until your target resolution. And we see that this actually does as well as if you were to train a model from scratch. And I'll show some results. So here are the validation losses for these different models. So we already saw that the coarse model is not capable of capturing the sharp gradients and flow instabilities in fine discretization. So its loss actually increases. The OSTL is the one-shot transfer learning, and it does a pretty good job of improving the validation loss. So we see almost a 2 to 7x improvement in the validation loss. But at the same time, when the validation losses, it's not resolution invariant. The loss is better, but it still increases as we increase the discretization or resolution. It still slowly starts creeping up. And this is to what I briefly alluded to earlier. If you look at the flow, so this is the nose of a non-symmetric airfoil. This is, the left one is the velocity profile at 64 by 256, and the right is at the 2K by 2K. You can see that where there's in the nose and also in the upper body of the airfoil, you see that there's a lot of divergence in the flow features between the low and the high resolution. So when we go from 64 by 256 by 2K to 2K in a single shot, even though the net one-shot transfer learning significantly drops the validation loss, it's still there's still some error that creeps up, right? It's not able to be resolution invariant. And one solution for this, and this is also because we only do the fine tuning for 1 to 2 epochs on a single geometry, on a single ellipse geometry, which is not similar to our airfoil. So one solution is we could do fine tuning for more number of epochs, or we could add more geometries to a test set. But this goes counter to our original idea where we want to keep the number of simulations we do at, or data collection we do at high resolution to as minimum as possible for this task of super resolution. So that's why we choose the alternative of incremental transfer learning. So the incremental transfer learning actually does much better. It drops the validation loss by another 3x. And the cool thing is that it reaches the same accuracy as the oracle. So here, in the B and the base model, or the teal line here at 256 by 256 and 5112 by 5112, is training a model from scratch using a large data set, similar to the coarse model, 64 by 256. We train a model, we collect data at 256 by 256, a large amount of data, and we train a full model from scratch. And this is the accuracies we get. And the incremental transfer learning is able to reach the same accuracy as that oracle, but using a fraction of the amount of data. So that is actually pretty positive here. So here, just to show you how much the data collection and training is reduced. So compared to the base model, for in the case of the training time for 512 or 512 is almost 38. So this is all in hours. So it's almost 38 hours. So compared to that, the incremental transfer learning can reduce the total data collection training time by almost 10x. And we didn't do this oracle comparison at 1K by 1K, 2K by 2K, because it becomes infeasible. We can start to see that the wins, they're starting to grow exponentially. And this is performance. I don't expect you to read this table, but the only thing to point out is that we tested this on different test cases. So all of these test cases on the left. So here below, I'm showing some of the geometries. So this is non-symmetric airfoils. So in the previous CFDNet case, we looked at symmetric airfoils where you have a sharp edge. But in the case of non-symmetric airfoil, the shape of the airfoil is also very different, not just the sharp edge. So that changes the flow field, especially the pressure is different in around this geometry compared to the symmetric case. And also we changed the theta angles, which an alpha angle, which is the angle of attack, and the pitch angle. So they're also varied. So we try for different configurations and different geometries. So all of these cases have never been seen by the model during training. And we observed that across the board, irrespective of the resolution or the test case, we see about a 2x speed up consistent compared to the physics solver. While at the same time, we reduce the training data set by almost 15x at the high resolutions. And this is to show the qualitative results. So you can see on the right side, this is for the non-symmetric airfoil. So this is for the airfoil here, shown on the left. We can see at the low resolution, the velocity, pressure, and the viscosity, there's quite a bit of, the flow is not fully resolved, and there's quite a bit of error. But taking this as the input, SURFNet is able to resolve the flow and get the same solution as our ground truth, which is our physics solver. So we're able to recover the solution entirely without any error. So the main key lessons from my first part are data-driven deep learning, these models, they show a lot of promise for accelerating our traditional numerical simulations with limited high-dimensional data. And they perform really well as accelerators for both generalizing and extrapolating without relaxing the physics solver convergence constraints. So today we can actually drop in these models as an accelerator and start using them in physical simulations. But if you want to use them as a pure surrogate, we are still quite a bit far away. If they were to entirely replace physics solvers, we are not quite there. And one of the main limitations is that they mainly surrogate a very specific realization for PDE, and they're very problem specific. And I'll talk a little bit more about what I mean by this. And also they are quite challenging to scale to large problems. So we see that even when our fine tuning, when we go to 2K by 2K, start trying to initialize the model and train on a single GPU node, it starts to become infeasible. So you need to start going distributed at that point to be able to train a larger model. So it starts to become more challenging. So this brings me to my second part. So how do we actually solve the holy grail where these models start to replace our traditional numerical solvers, and they can be transferable? By transferable, I mean solve flows on unseen domains, unseen shapes, unseen boundary conditions, similar to how our numerical methods can do today. And this is joint work with a group at UCS. My former PhD student, Hanjay, who recently graduated, now is at Lawrence Berkeley Labs as a postdoc, and another PhD student, Robert, and my colleague, Rami, in the mechanical engineering department at UCI. So I previously mentioned that the limitation of the current models is that they learn a specific instantiation of the PDE. So here in all of these cases, these different types of models, they have their trade-offs, but fundamentally they all approximate a function that maps your data from one finite dimensional space to another. So here, let's take, for example, a boundary value problem. This is a simple Laplace equation where you're trying to surrogate u of x on some domain omega, given the boundary condition or boundary value function g of x. And each time this boundary function changes or this domain shape changes, these models have to be retrained. And in each case, the deep neural network need to learn to approximate a new function. And this is not really feasible if you want to have a universal approximator. So there's currently no mechanism for estimating the solution of a PDE system given a pre-trained neural network model without retraining or fine-tuning. Okay. And recently there have been an extension to this function approximator. So now 2 papers that came out last year where they now learn how to approximate not just functions, but operators. So operators essentially map from function space to function space. So instead of doing a finite dimensional map, this is an infinite dimensional map. And in theory, yes, these deep neural networks can approximate operators. They can solve a whole family of PDEs at once, given a range of initial and boundary conditions. But the problem is that if I change this domain shape, if I change the shape of the domain, then these operators still need to be retrained because they only work on fixed domains, even if they can handle different boundary conditions. So we still are lacking neural network surrogates that can solve PDEs in unseen domains with unseen shapes. So not just square or rectangular shapes, but let's say I have a step shape. How do I take a neural network model that was trained on, let's say, a square, and then apply it to a step flow? So this is still a problem that is unsolved. And I think until we actually crack this, we won't be able to build surrogates that are truly scalable for large domains and that can compete with our traditional numerical solvers. So, and this is where our ambitious second part of the project comes in, where we design another framework that essentially tries to leverage deep learning to build transferable surrogates that can solve PDEs in these unseen domains with arbitrary boundary condition. And the key here is that we decouple the problem. So there is the issue of trying to predict for arbitrary boundary conditions. And then there is the issue of trying to predict on unseen or random shaped boundaries. So we decouple these two problems, right? So first, the idea here is we decompose the domain. So here is a domain that says Mosaic flow. So we decompose this domain into smaller subdomains, call each of these smaller subdomains. So here is one small subdomain here of size 1 by 1, call this a genome. And then we predict the flow in this genome using a pre-trained deep neural net. So call this network a genomic flow network. And the idea is that this genomic flow network should be able to solve this BVP, boundary value problem, with any arbitrary boundary condition, but on the square domain. So it's still not, it cannot predict on arbitrary shaped domains, but it can predict for arbitrary boundary condition on the square domain. So now we can do this prediction on all of these subdomains. So the question is, how do we now actually find the solution on this larger domain? So that's the second part of the problem, where we compose these GFNet inferences to make the inference on the larger domain. And this large domain can be any shape, size. And we do this using what's known as Mosaic flow predictor. So this combination or the composition of all of these subdomains is a mosaic, call this a mosaic. So the algorithm that actually composes is called a Mosaic flow predictor, and it's an iterative algorithm, and I'll talk about that. So that's kind of the high level idea. So why does this mosaic idea actually work? So let's say if your BVP, the boundary value problem, is well posed, is considered well posed, if the solution U is unique given this boundary function G of X. So given that for such a boundary value problem, right, if I were to take this domain and decompose this into two subdomains, so here the domain omega is split into two genomes, omega 1, omega 2, and they have the shared border in the middle. If my solution U is unique on this larger domain, then my solution is also unique on this smaller domain U1 and U2. And to find U1 and U2, and it's well posed, and to find U1 and U2, we need to solve two boundary value problems, one on each of these domains. But the challenge here is that to do that, we need U on the shared border, which we don't know, right? So this is unknown. So how do we actually solve this problem? So we do this using iterative strategy. So initially we randomly assign values on the shared border, and then we solve U1 and U2. And then we use this solution to actually update our initial guess and then repeat until convergence. So this is kind of, if you're familiar with the standard halo exchange in a shared border, this is similar to how we update that. And when we do that, we see that, okay, we take about, for this very simple problem, with just two genomes and one shared border, it takes about 300 iterations to converge to the final solution. This is fine, but the question is, can we do better? So what we actually do is, so we decompose the genome, decompose the domain into genomes. So we call this original decomposition, basic genomes. And then instead of doing this iteratively trying to do halo exchange, what we do is we place another auxiliary genome that overlaps with the shared border, right? So the idea is that this approach, it introduces a stronger and more effective coupling between these basic genomes. And we see that this significantly accelerates the rate of information propagation. So in this case, we can reach convergence fast by fact 12x faster than if we were to use a traditional halo exchange. And also the cool thing here is that now we don't need to use, we can just use the same GFNet to do predictions for both the original genomes and also the auxiliary genomes, and then do iteration. So we can just use the model without using, as a pure surrogate, without having any physics solver involved. Okay, so how does a GFNet get trained? So here our goal is that we train the GFNet on a square domain, a small domain, and it needs to be able to estimate the solution anywhere inside this genome for a range of boundary conditions. So the input is that it takes the discretized boundary function G and also X. These are two inputs to the network, and the output is essentially G times X, where here G represents the discretized version of the genome, and X is the coordinates where we want the prediction of U of X. So here, NBC is the number of points in the genome's boundary. N bar is the number of variables we want to predict, the flow variables, and NDIM is the spatial dimensions that we want to solve. So the way we generate the input is that we solve the PDE with realistic boundary conditions on a large domain. So here I'm showing you a large domain. And what we essentially do is we extract. So if our genome is essentially much smaller than the domain that we want to predict, so we can then place the genomes inside and then extract the solutions. That's how we generate the input. So here, this is a flow in a lid-driven cavity, which is swept by the genome, where we record the flow. And we also record the value of the boundary. Since at any point inside the domain, the solution is still well posed, we can actually take these boundary conditions on these genomes, and they form correct solutions for our input. And the loss here is a combination of 3 different losses. So the first L1 is the data loss. This is the typical. We want to make sure that the network is able to predict solution on the available data. And the second is a residual loss. So here's where we enforce the surrogate to satisfy the PDE on some selected points. So in the case of the data loss, since our input comes from the physics, the numerical solver, which is typically on a grid, then the boundary and the data points are well equally spaced. But for the residual loss, we can actually choose the points adaptively. So these points are called the collocation points. And the way we choose them is to look at the magnitude of the gradient magnitude. And we essentially put more points where we have a large gradient. So this is the points we actually want to make sure that we reduce the error. And then the third loss here is some regularization loss, and we have to actually control these. And I'll show you that for some equations, the residual loss actually does not result in a better model. In some cases, just training with the data loss gives us a much better model than residual loss. I'll briefly mention that. So what is a GFNet architecture? So we essentially came up with 2 different types of architectures. So for linear PDEs, such as Laplace equation, our solution U of x, it's essentially a linear combination of our boundary function values. Okay. So in this case, the solution can still be non-linear, even if our boundary function is actually a linear function. So to preserve the linearity, what we do is we pose a linearity preserving fully connected architecture. So the idea here is we take our input x and we pass them through multiple fully connected hidden layers. And we set the last hidden layer h to have the same size as our boundary function. And then to preserve the linearity, what we do is the output is essentially just a linear combination of g and h. So with this configuration, the nice thing is that we kind of preserve the linearity of PDEs such as the Laplace equation. And we see that this architecture actually gives us a much better accuracy than if we were to also pass the boundary function g into the network, as we would do in the case of nonlinear PDEs. So in the case of nonlinear PDEs, such as Navier-Stokes equations, we typically just concatenate the boundary function and the input x, and then into one input array, and then pass them through these hidden functions. And this architecture does much better. So depending on the type of PDE, the architecture is kind of modified to tailor to that PDE. And we see this gives us much better accuracies than using one standard architecture for all types of PDEs. And since we only need to train the neural net once, this works pretty well. Spending time to actually tailor the architecture it's useful. It's useful time spent. So so once we have the GFNet trained, so given some domain, so here I'm showing you a slightly different domain. So this is a domain of size 2 by 2, and we have 4 basic genomes, the genomes of size 1 by 1. So we do the prediction on these basic genomes, and then we have auxiliary genomes, so in this case G5, G6 to predict this shared border, G7, G8 to predict this horizontal shared border, and then G9 to predict the solution from these 2 genomes. So essentially the idea is the number of auxiliary genomes is variable. It can be chosen. The basic genomes can also overlap. Here, we're just showing an example where they don't overlap. And then the auxiliary genomes can be placed anywhere. So anywhere where a solution we need to improve, we can actually place the auxiliary genomes. And also the number of genomes, auxiliary genomes we place, there's a trade-off between that and how fast we converge to the solution. So there's some trade-offs here to be analyzed. So here I'm showing you, after we do this, this is one iteration using these 9 genomes. You can see that there's a lot of error in the center where we do random guesses initially, but after one iteration, we've improved the solution, and then we keep doing this, and after about 18 iterations for this particular example, we converge to the exact solution. So this actually works pretty well. And for the case that I showed earlier, which is a much larger domain, so this domain here is about 1200x larger than the training domain. So this is training domain is of size 1 by 1. This larger domain where we're trying to predict the flow is significantly larger than where the genome was actually trained. And in this case, we used about 2020 total genomes, basic and auxiliary, together to do the prediction. And this whole prediction took about less than 3 hours to converge. So some performance numbers. I'm almost done here. So some performance numbers. So here we are comparing this is for the Laplace equation. So we're comparing this against PIN. PIN is the physics-informed neural nets, and for 2 different boundary conditions. So here they both were trained at a 1-by-1 domain, and then we can see that PIN does actually pretty well for simple boundary conditions, but when we have complex boundary conditions, it starts to fail, especially at large domains. Whereas the Mosaic flow predictor, it does pretty well for large domains. And in this case, I should mention that the PIN is actually retrained for every new boundary condition, whereas the Mosaic flow predictor, it has never seen any of these boundary conditions before. And this prediction is happening without any retraining or fine tuning. So it's just using a pre-trained neural net only. And if you look at the time, we see that the PIN is several orders of magnitude slower than the Mosaic flow predictor, because you need to retrain the model for every new boundary condition. And we are able to scale pretty well. The interesting thing is that with both single and double precision, we get pretty much identical results. So it looks like this is actually positive, because we can, unlike traditional numerical solvers, which typically require double precision, we can get away with just single precision. We haven't tried something like half precision, smaller than single, but that's something that is worth investigating. So how mixed precision can be used to further improve the time to convergence. And more interesting is the Navier-Stokes equation. So this is a flow in a lid-driven cavity. So in all of these, except in the top case, we're changing the velocity. So the velocity keeps moving with the lid. And this is the ground truth from the open form simulation. And we see that if we use the 9 genomes that I showed earlier, we get a prediction, but it doesn't quite converge. But if we add a few more, add 10 more auxiliary genomes, we have 19 genomes, then we are able to predict. And this is using boundary conditions that has never been seen during training. And we're able to do this prediction in under 2 minutes. Whereas the PIN, it fails to resolve the flow even after retraining with the new boundary condition for 2.5 hours. So we're very excited to see these results. And what's even more exciting, made us jump out of our chairs, is when we actually change the shape of the domain. So the flow, this is a flow in a step-shaped lid-driven cavity. So here the training, here I'm showing you the training samples. Training was done on a genome of size 0.5 by 0.5, whereas what we're trying to predict, this shape is about 12 times larger than the basic genome. So this was decomposed. I'm not showing the decomposition, but we have about 12 basic genomes and 21 auxiliary genomes for this prediction. I don't know what I did, but just ignore the line. And this is the velocity magnitude of the ground truth. And we see that the MF predictor, it predicts the magnitude quite well. And these are the streamlines. And here I should point out that there are 3 different vortices, and the training has never seen 3 different vortices at all. So the training is done on these very small shapes. It hasn't seen any vortices at all. So given that it's able to capture all these 3 interrelated vortex structures that is never seen during training. So looking forward, so this is pretty exciting, and we think it's very promising direction with the CFDNet and the Mosaic flow predictor in trying to scale these surrogates to large domains of different shapes and boundary conditions. So looking forward, a couple of different questions that we want to look at is, so far what I showed is the training of the genome is done on the square 0.5 by 0.5 or 1 by 1 domains. So when we have curved objects as an airfoil, then the square genomes might not be as accurate. So how do we actually encode the shape of the boundary as well, so the CFDNet can predict on curved domains is one interesting future exploration. And what I showed you is mostly for steady state. So if you want to do like unsteady simulations, how do we add time to the framework? And when you add time and you add the coordinates of the shape, then you start to have a lot of different inputs. So your network starts to blow up. So how do you actually encode all this information while still keeping the number of input dimensions to a minimum is another challenge. And what about other neural net architectures? So we use CNN and fully connected layers, and even, but what about transformers and other newer architectures? Can they be used for training the GFNet more accurately? That's something to explore. And I talked about an iterative algorithm for predicting the shared border. But instead, what if you were to use something like an optimization? So instead of having auxiliary genomes, what if we made these shared borders also trainable, and or use reinforcement learning? So other ways of predicting this missing information. And the cool thing about the Mosaic for Predictor is we can do the prediction on these different subdomains in parallel. So if you were to, so how do we actually use distributed inference, especially to scale to large domains, and also how do we extend this to 3D, uncertainty quantification, and so on. So a lot of interesting, it's just the tip of the iceberg. It's a lot of interesting problems to still explore. So thank you for listening to me for almost an hour. If you're interested in more details, these are two of the papers that are both available online that I kind of talked about today. And I'm happy to take any questions.
Okay, thank you, Aparna. So we'll move to questions in just a moment. Before we do, I just want to give a brief ad for the next SPCL BCast, which will be on the 20th of May at 6 p.m. Zurich time, so same time as this one, where we will have Sunita Chandrasekaran from the University of Delaware speaking.